Hello everyone, so here we have a Eastern Cape, grade 11, November 2022, physical science chemistry exam. It is 100 marks and should take you 2 hours. You can download it by clicking the link below, and then you can fast forward to the specific parts that you need to practice. Or you can just go through the whole thing with me. Which one of the following is the name given to the reaction in which electrons are transferred from one substance to another? Well, we know there's a specific chapter that we've done in grade 11 where you've got one process where electrons are released or given away, and then we've got another type of system where electrons are gained, and that is redox. We know that redox means reduction and then oxidation. That's where the name redox comes from. Now we know that reduction, from the acronym oil rig, we know that reduction is the gain of electrons, and then this one is the loss of electrons. So one of these substances is gaining electrons and the other one's losing them. So they're moving electrons. For example, here you have this substance which is being oxidized. So oxidation is when you lose electrons. And then we've got another substance over here which is being reduced. And that's when you gain electrons. So we've got one. So it says here, which one of the following is the name given to the reaction in which electrons are transferred from one to another? It's redox. So it's A. The diagram below is used to demonstrate the difference between interatomic and intermolecular. Okay, this is a good question because a lot of learners get confused. So let's say we have a molecule like this. Now this is one molecule. Now these bonds over here, they are keeping the molecule together. They are inside this molecule. They are inside. So they are called interatomic, or another name is intramolecular. Okay? But now if I had to draw another one, then there are also little forces in between these molecules. So they're not these are between two different molecules now. Now those forces that are in between the molecules, those are called intermolecular. Not intra, so that's an A over there. Not intramolecular, it's intermolecular. So it says here, okay, so if I had to ask you, that one over there, that is an intermolecular, so it's inter. And then this one is an intra. Okay, so it says here, and by the way, these ones over here that are inside the molecule, they are much stronger than these ones that are in between the molecules. Okay, so we can say that intramolecular, much stronger than inter. Why is that? Well, these ones are the ionic, metallic, covalent. These ones are the dipole-dipole, London, hydrogen bonding. Okay? So, let's see which of these is correct. So, X is stronger than Y. Well, no, because X is an intermolecular and Y is an intramolecular. So, these ones are much stronger. Those are your ionic, covalent, metallic. B, let's see. X is a interatomic. Nope. X is an intermolecular because it's between the molecules. C, X is an intermolecular force. Yes, that is correct. Let's just check D. Y is an intermolecular force. No, it's not. Y is an interatomic or intramolecular. Not inter, intra. Make sure you understand the difference between inter and intra. Okay. The minimum amount of energy needed for a chemical reaction to start is called... Okay, so this is just your activation energy. So remember, we've had those enthalpy diagrams which look like this, and then it goes something like that. And these are your reactants over here. These are your products. And so to get these to go from reactants to products, you first have to raise the energy. So you have to get them from here up to here. Okay? And so that amount of energy from there to there is called your activation energy. This place over here at the top of the mountain, that area is called the activated complex. But they want to know what is the energy to start the reaction. It's called activation energy. Consider the potential energy diagram for this hypothetical reaction, and then it says what is the heat of the reaction. Okay, so heat of reaction in a diagram like this is the H of your product, the energy of your product, minus the energy of your reactant. So remember, this part here is always your reactant, and then this part here is your product. So what we can do is we can say product, which is X, minus this one, which is your reactants, that's going to be Y, and so it's X minus Y. So the answer is B. Consider the incomplete reaction below. Which one of the following is correct? Okay, so you know in acids and bases, we've got all these different reactions. We've got an acid plus a metal. So if it's just a metal, then we should know from theory that that gives us hydrogen gas plus a salt. If you have an acid plus a metal oxide, then it gives you salt and water. If you have an acid plus a metal hydroxide, then it also gives you a salt and water. And then if you have an acid plus a metal carbonate, then it gives you a salt, water, and carbon dioxide. So if you're producing a salt and water, then it can only be either this one or this one. So here they have metal oxide, so it's definitely going to be that one. Consider the substances P, Q, and R. P can dissolve in Q, but not in R. Okay, so let's quickly talk about how dissolving actually works. What happens when something dissolves? So if you have, let's say you've got water, for example. Okay, so you've got a glass of water here, which is H, O, and H. Now, we know that the H's, let's actually put another one. We know H's are positive, and the oxygens are negative. Okay, just from electronegativity, polar, non-polar, dipole moments, all these like things from that chapter. Okay, so obviously these hydrogens are positive, these ones are negative, and this one's positive. Now, let's say we take like some table salt, for example, okay, which is NaCl. Now NaCl is bonded with ionic bonds, okay, because we have a metal and a non-metal. And if you had to look at the electronegativities, then if you look at Na on the left-hand side, you can see it's got an electronegativity of 0.9. If you look at Cl, it is 3.0 for its electronegativity. So if you minus them, it's 2.1. And also we know that sodium is on the left-hand side, so it's a metal. Chlorine is on the right of the periodic table, so it's a non-metal. And so we've definitely got some ionic substance going on over there. Now we know that from electronegativities that Na is going to be more positive. Okay, so Na is more positive and Cl is more negative. Okay, so when you throw some NaCl into this solution, so here you would have NaCl, what happens is that all the oxygens, they get attracted to the positive sodium ion, okay? And all of the hydrogens get attracted to all of the negative chlorine ions. And because there are so many water molecules surrounding the NaCl, it starts to pull the Na and the Cl apart. It actually breaks this ionic bond. And then what you have is a dissolved NaCl, which would look like this. So you would have the Na being surrounded by a whole bunch of water molecules with the oxygens facing it, because the oxygens are negative. So that's what you're going to have. And then you're going to have Cl's being surrounded by also water molecules, but facing like that, where the positives are closer. You see? And so that is what dissolving is. Dissolving is when you take something like that, that's ionic, for example, you throw it into, for example, water, and you've got this attraction between them. Now let's talk about the name of that attraction. Well, it happens when you have a polar molecule. So you need a polar molecule, and then you need an ion. Okay? Now a polar molecule, we also refer to it as a dipole. So we're going to say that this is an ion dipole force. And that is a type of force that we've learnt about, which helps us to dissolve things. Okay? So I would imagine that P and Q would be some type of ionic substance and a dipole substance. So this one could be the correct answer. Yeah, it would have to be this one. And then R is a London. It's got London forces, which means that this is a non-polar molecule. So what that means is the following: if you take a substance like R, which has London forces, it means that these molecules are non-polar. So let's take a non-polar molecule like A. It's just a made-up molecule, AA. So because these are the same, there's no positive or negative. So it's just like that. Okay? Then all of a sudden you throw in some NaCl. Okay? NaCl, which is positive and negative. These AA atoms are not going to be attracted to the NaCl because there is no positive and negative in them. So why would they be attracted? And so there is no forces that are going to be pulling on the NaCl, and so the NaCl is not going to be able to pull apart. So it's not going to be able to dissolve like we saw over here. So A makes the perfect sense. According to the kinetic molecular theory, molecules of gases at the same temperature will always have the same what? Okay, so remember, let's look at a container that has a high temperature and then a container which has a low temperature. What does it actually mean? Well, in a high temperature, it means that the molecules are busy moving extremely... Okay, I'm not even going to try to be like a textbook and show fast and slow. I don't know how these guys do it. But these molecules are moving really fast, okay? They are moving rapidly, okay? Whereas these ones are moving very slow, okay? These ones are moving very slow. So, when the molecules are moving fast, we say that they have a high kinetic energy. Kinetic energy is just movement due to the speed and the mass, but you can think of it as just as the movement and the speed. Okay, and then these ones have a low kinetic energy. Low kinetic energy. So, temperature, what is temperature actually? The definition of temperature is not how hot it is. It is a measure of the average kinetic energy of the molecules. So if there's high temperature, then most of the molecules have a high kinetic energy. If it's low temperature, then most of the molecules have a low kinetic energy. So this answer is going to be D. With this question, we will be splitting the questions up onto individual pages, but let's just have a look. They say consider the following compounds. So we have oxygen, water, and then H3O+, which is hydronium. So the first one says define the term molecule. Okay, so let's talk about what a molecule is. So let's say you have a single little circle like that, and it is H. Now, when it's a single little thing like that, we call that an atom. Okay? Now, if you put two of those together, they can be the same or they can be different. So let's say we put another one of H, or you could have something like H and then another one which is like Cl. As long as you have two or more, that's a molecule. If there's only one, then we just call it an atom. But as soon as you have two or more, then, for example, we could have CO2, which would be like 3 atoms, CO2. Then that is also a molecule. So there we have it. It is a group of two or more, okay, so two or more, like we said, covalently, yep, these are all covalently bonded, that function as a unit. Okay, now we're going to do some Lewis diagrams. So the first one, they want us to do the Lewis diagram of oxygen. Okay, so we need to get our periodic table. So here I've just cut the top part of the periodic table off because we only need it for oxygen and hydrogen. Okay, so here are the steps that you can use to do a Lewis diagram. Okay, so it says that the first step is to count the valence electrons. So what do we mean? Well, in this first example, we have oxygen, okay? So that means we have two oxygens. So we go to oxygen on the periodic table, and we count the valence electrons. So you count the group number. So 1, 2, 3, 4, 5, 6. Okay? So that means that there are 6 valence electrons for oxygen, but we have 2 oxygens. So 6 times 2 is 12. Okay, so that's step 1. Count the valence electrons. And you do that for every atom. This one says, put the least electronegative atom in the middle. Okay, but now we only have 2 oxygens, so you can't have a middle atom. So there we just put them next to each other like that. Okay, so that's step 1 done, step 2 done. Place bonding pair of electrons between all atoms. Okay, there's a bonding pair. Okay, so we've done step 3. Place all the remaining pairs on the outside atoms. Okay, well, we only have 2, so they are both considered to be the outside. So you can just put them in pairs of 2, like they said. And you keep going until you have no more electrons. So we only have 12. So 2, 4, 6, 8, 10, 12. Okay, so that step's done. Okay, so you wouldn't just go there because then you're using too many electrons. Step 5, move the pairs around so that you can achieve the octet. The octet tells us is that you need to make sure that the atoms have 8 electrons around them. Obviously, there are exceptions. For example, hydrogen does not obey the octet rule, and there are other exceptions, but it's like 1 or 2 others. But the main one is that hydrogen does not need 8, it only needs 2. So what we can see here is that this oxygen that we have on the left is surrounded by 8 electrons. So that's good. That's an octet. Octet means 8. But if you look at this oxygen, it is surrounded by 6. So what we can do is you take any of these pairs, just take one of them and move it to the inside. So I'll take this one and I'll rather write it over there. Now all of a sudden we can see that this oxygen is still surrounded by 8, but this oxygen is also surrounded by 8. And so that is perfect for that diagram. And yes, it doesn't really matter if these electrons are written there or if you put them there. That doesn't really matter. Okay, so let's try this one over here. So we go and we count the valence electrons. So this one has 2 hydrogens and 1 oxygen. So each hydrogen has 1 valence electron. Okay, so if we have a hydrogen, and an oxygen, this one has 1 valence electron, this one has 1 valence electron. If you count for oxygen, it has 6 valence electrons, so we have 8 valence electrons in total. Step 1, complete. Number 2, put the least electronegative atom in the middle. Okay, so we're going to put oxygen in the middle, and then hydrogens on the side. The reason is that we normally put the least electronegative atom in the middle. Now, hydrogen has an electronegativity of 2.1. Oxygen is 3.5. So technically, hydrogen has to go in the middle. But the rule says, except hydrogen. So when there's hydrogen, put them on the outside. Step 3. Place the bonding pair of electrons between all atoms. Okay, so we put a bonding pair between all atoms. There we go. Now, place the remaining pairs. Now, think about this carefully. We only have 8 electrons in total. We've already used 4. 1, 2, 3, 4. So it says, place the remaining pairs on the outside atoms. Okay, so let's try this question now. I've modified the notes. I forgot that this step 4, I've just added that over there. Okay, so because it's going to be useful for this next one. So step 1 says go count all of the valence electrons. So we know that we've got 2 hydrogens, so let's put 2 hydrogens and an oxygen. Let's go get the valence electrons. So for hydrogen, or let's not do that, you're going to think it's electrons. So let's put lines. No, let's just do. Okay, so this is in group 1, so that's got 1 valence electron. And then oxygen is in group 6, so that's got 6 valence electrons. If you add those numbers together, there are 8 valence electrons in total. Then with number 2, put the least electronegative atom in the middle. Okay, so can you see that hydrogen has an electronegativity of 2.1, whereas oxygen has an electronegativity of 3.5. So technically hydrogen should go in the middle because it said put the least electronegative atom in the middle, but it says except hydrogen. So we're going to put oxygen in the middle and we put the hydrogens on the outside. The hydrogens always go on the outside. That's step 2. Step 3, place a bonding pair of electrons between all atoms. Okay. There we go. Place the remaining pairs on all of the outside atoms. So how many electrons do we have left? Well, we have 8 in total, and we've already used 1, 2, 3, 4. So we still have another 4 electrons, or another 2 pairs if you think about it like that. So we can place the remaining electrons in pairs like that. We didn't put them on the hydrogen. Normally you would have put them on the outside atoms, but they said except hydrogen. Now number 5. Move the pairs around to achieve octet. But we don't need to do that. We already have octet, or the octet rule, because hydrogen only ever needs to have 2, and these hydrogens both have 2, and then oxygens need to be surrounded by 8, which they are. Now, you could leave it like this, or you could also write it in the proper way for water, which is actually like that. But they won't penalize you if you leave it like that. The H3O plus, which is hydronium ion, forms when the oxygen atom in H2O donates its lone pair of electrons into the vacant orbital of H plus. Okay, so what are we talking about here? Let me explain. So in a normal bond, and listen up guys, this is quite important, but it's not too difficult. If you have a normal bond, okay, let's say you had hydrogen, okay, and let's say you have chlorine. Now, hydrogen has 1 valence electron, so let's put that over there. And chlorine, or let's actually use fluorine instead, because we've got it here on the periodic table. If you look at how many electrons fluorine has, it's got 1, 2, 3, 4, 5, 6, 7. It's got 7 valence electrons. Let's go put them down. 1, 2, 3, 4, 5, 6, 7. Okay. Now, when these two decide that they are going to bond, it's really simple. All that happens is that this hydrogen just slides in over there, and you produce this. Okay? So the important thing I want you to understand is that this is the way bonding normally happens, where if you look at the bonding pair of electrons, 1 electron came from the one atom and the other electron came from the other atom. So they are sharing, and it was an equal, they both added 1 electron to the bond. That is the way it normally works. But there are situations where it does not work like that. An example would be the following. Let's say we have NH3, which is ammonia, okay? So if you had to go do the Lewis diagram, you would see what I'm talking about. But what you're going to end up with is the following for NH3. And then it's got this lone pair over here. Okay, so that is how NH3, that's the Lewis diagram of NH3. Now, let's take something else. Let's take a hydrogen ion. Listen to that carefully. So it's a hydrogen, but it's the ion form. So it's the H+. So you got to think about this one carefully. If you look at normal hydrogen, okay? Normal hydrogen. How many electrons does normal hydrogen have? Well done if you said it just has 1. If we see on the periodic table, we can see it only has 1 electron. So if you take that electron away, it turns into a positive ion. But then how many electrons does it have if it's the ion form? Well, now it's got no electrons. So a hydrogen ion has no electrons, not even one. Okay, so let's say these two things are floating around, and this hydrogen ion notices, hey, look over there. There's 2 electrons. What if I just swoop on in there and simply bond like that? Well, that does actually happen in real life. Now, what we must understand is that this hydrogen ion was positive, and this ammonia was originally neutral. So if you add something positive over here, then this whole molecule would become positive. Now, we need to understand that this bond over here, those 2 electrons, where did they come from? Did one of them come from hydrogen and one of them came from nitrogen? Did they both come from hydrogen, or did they both come from nitrogen? Well, remember, it was originally like this. That's what we originally had. And then this hydrogen ion, which has no electrons, just decided to go and join there. So can you see the difference between this type of bond, where both electrons came from one atom, compared to this type of bond, where one electron came from one atom and one electron came from the other atom? So when you have both electrons coming from one atom, we call that a dative covalent bond. Okay, so let's go do this next question. Okay, so we're going to draw the Lewis structure of H3O. So let me show you how H3O ion, don't worry, this is not a minus, by the way. They're just trying to say that it's the H3O positive, and then for some reason they're just saying ion, like that. They could have just said that. Okay, so let me show you how it forms. You take a water molecule, which, if you go do its Lewis structure, looks like that. Yes, you might also do it like that, which technically isn't wrong to do it like this, but just be careful when you are dealing with the VSEPR theory, where they talk about the different shapes, or where they talk about things like that, where you don't want to call this a linear molecule. Remember that H2O is actually like that, so we give it the name angular or bent. Okay, and if you label it like this, you might even say that it's non-polar, but it's actually like this, which makes it polar. Okay, I'm getting into a little bit of deeper theory now on other topics, but just remember that. Okay, so this is a water molecule. Then, if you take a hydrogen, now remember, hydrogen has 1 electron, but we're not talking about a hydrogen. We want to talk about a hydrogen ion, okay? So that means that it's lost that 1 electron, so it has no electrons. You must think about that. That's quite interesting. Hydrogen only has 1 electron. It is the only atom that ever has that. And then when it loses that electron, it has no electrons. That's not normal. Like everything else, anything else, if it had to lose an electron, it would still have 1 left. But when hydrogen loses that electron, it's got nothing. So what happens is that this hydrogen decides to go link up either over there or over there. And it doesn't need to have its own electrons because there are already 2 waiting for it, either there or there. So let's say that it decides to link up over here. Now remember that this whole structure, because originally water is neutral, and then you're adding something that is positive to it, and so this whole structure is now positive. Which molecule is polar? Okay, so let's quickly go check this out. So we drew the Lewis diagrams of both, remember? So with oxygen, we drew it as, we had this over here, and then we had something like that. Yes, some of you might have put these over there. It doesn't really matter. Okay, so that's oxygen. Then water. So remember, you can draw water like this if you want to. But remember that that's not really what it looks like, and it could get you into a little bit of trouble, not from the teachers, but like it might cause a bit of confusion for you, because you might think that this is a linear molecule and you might start calling it non-polar, but it's actually like this. Okay, now let's get a little bit deeper into this understanding here. So let's go get our periodic table. And let's go examine this part over here. Okay, so the electronegativity of those oxygens is 3.5. So this one is 3.5 and this one is 3.5. So because they have the same electronegativity, these electrons in the middle, they are not going to be a little bit more to the left or a little bit more to the right. Because remember, electronegativity is how strong can the atom pull on those electrons, okay? But these two are equal, obviously. So these atoms are just, these electrons are just going to stay in the middle. And so this molecule, is it going to have like a more positive part and a more negative part? No. So it's going to be non-polar. Polar means it has like a more positive part and a more negative part. Okay, now if we look at this part over here, which is water. Now hydrogen has an electronegativity of 2.1. Okay, 2.1. Oxygen is 3.5. What that means chemically is that oxygen loves electrons way more than hydrogen loves electrons. The more the electronegativity, the more electrons it just wants electrons, okay? It loves electrons. So these bonding electrons over here are actually not going to be in the middle like this. They would actually be closer to oxygen and over here as well. Okay, so all of these electrons, they absolutely just love oxygen. Because of that, oxygen becomes slightly negative. Like permanently, it just becomes negative because the electrons are just chilling there, okay? And then because these hydrogens have almost lost their electrons, they haven't lost them completely, but it's almost like they've lost their electrons, they become more positive, okay? And so what we see in this water molecule is that it's going to have an overall positive part and an overall negative part. Now, let me explain something. What your teacher might have shown you in class is that the electrons are going towards oxygen. So your teacher might show arrows like this, and then the electrons are going towards oxygen. So if you have an arrow going this way and you have an arrow going that way, then overall the arrow should be going like that. And we call this a net dipole moment. It's got a net dipole moment. Okay, so it's definitely a polar molecule. But there are some learners who still draw water like this. And then what they do is they're like, okay, if these electrons are going this way and these electrons are going this way, then surely they cancel out, and so the molecule is non-polar. That is the problem of drawing it like that, okay? And that's why you need to remember that water does not look like that. It actually, in real life, it looks like that, okay? Right, so we haven't actually answered their question, but I just wanted to explain. Okay, so let's try explain. So which molecule is polar? We can definitely say that it is water is polar, okay? Okay, so what we could do is we could say that with oxygen, okay, so we get 1 mark for just saying water, okay? Now we could say that in oxygen, the electronegativity difference is 0. Okay, now with water, we can say that the OH bonds are polar. Let me talk about that, because you see how we had water. Okay, now this one had an electronegativity of 2.1, this one had an electronegativity of 3.5. So that is a polar bond because the electrons are going to be more towards this side, causing this to be more positive and this to be more negative. That is a polar bond. But having a polar bond does not mean the whole molecule necessarily is going to be polar. I'll give you an example. What about CH4? CH4, which is methane. So, hydrogen is 2.1, carbon is 2.5. So can we agree that this bond over here is definitely polar, because this is more positive and this is more negative? So that's polar, so the electrons would go towards there. But can you see that overall all of those arrows would cancel out? And so what we would say with this kind of molecule is that it's got polar bonds. Yes, each bond is polar, we can agree on that. But overall, it is a non-polar molecule. So this one is polar bonds, but it's a non-polar molecule. Okay, so what we've just said here is that the OH bonds are polar. That is not enough though. That's like saying the CH bonds are polar. That doesn't mean much. We then need to say that the shape of water is, now your teacher might use the word angular or bent. What that means is that water does not look like this. It means that water, because if water did look like this, right, then we would say that it's non-polar, because look at those arrows, they would cancel out. That's a big mistake learners make. So some of you might be like, yeah, but Kevin, why, bro? Like, why is water not like this, but these molecules are? Guys, it is because of these lone electrons. They cause this like repulsion in the molecule. Remember, we're looking at this at a 2D view right now, but in real life these things are in 3 dimensions. And in real life these electrons, these lone pairs, orientate themselves in a specific way that causes the molecule to bend. Okay? And so because of that bent shape, if you now look at these polar bonds, you can see that these two lines are actually not going to cancel out, and this whole molecule does not become non-polar. It actually stays as a polar molecule. So the shape of the H2O is angular or bent. Okay, and that's it. So they're giving you 1 mark for saying that the water is the answer. You need to mention something about the oxygen, okay? Then you need to say that, mention something about the OH bonds being polar, and then also refer to the shape. Because remember, it is not enough to say that the bonds are polar, because you could have polar bonds, like here, but you still have a non-polar molecule. But when you look at the shape, we see that it causes the overall molecule to be polar. I will break these questions up onto different pages, but in case you just want to try all of them, there they are. So we see here that the table below shows the relationship between melting points of 3 molecules. Okay, so we've got CH4, CF4, and CCl4, and we've got their different melting points. First question says, define melting points. Now, guys, I wish we could just say that it's the temperature when a solid turns into a liquid, or boiling point is the temperature when a liquid turns into a gas. But we're not allowed to say that. Let me give you some theory here. Well, not theory, but like I'll help you with melting point. So we can say it is the temperature when the space and space phase are in equilibrium. For melting point, it's when you're going from solid to liquid. So you could say liquid and solid, or solid and liquid. So it's just when those two phases are in equilibrium. Explain the trend in melting points of the molecules in the above table by referring to the intermolecular forces and energy involved. Okay, so remember, intermolecular, those are the forces that go between the molecules. Those are things like London, dipole-dipole, hydrogen. Okay? If they said intramolecular, if they said intramolecular, or if they said interatomic, that's when we're talking about ionic, covalent, metallic. Okay, so explain the trend in melting points by referring to the intermolecular forces. Okay, for 4 marks. Okay, so let's start with CH4. So what we'll do is we'll go draw CH4, and we'll draw 2 of them. Why? Well, because we're looking at intermolecular, so you need to have at least 2, because you need to see what's happening between the molecules. We're not looking at what's happening on the inside. Those are covalent, ionic, metallic. We're not looking at that type of stuff. We're looking at what's going on between them. So the way we do this is we need to know, is the molecule polar or non-polar? Because then it's easy. So if you look at this, so if we look at the electronegativity of carbon, it's 2.5. And if we look at hydrogen, it's 2.1. So the electrons are definitely going to be more attracted to carbon. Remember, the higher the electronegativity, the more electrons are... so if an atom is more electronegative, it means it attracts electrons more. Okay? So these electrons are going to be more towards that side, there, and there. Okay, so we can definitely say that this bond over here is a polar bond. Polar means that there's a more positive part and a more negative part. However, this entire molecule is going to be non-polar. Why? Well, if you just look at all of those arrows, I mean, you've got an arrow going there, an arrow going there, an arrow going there, an arrow going there. They're going to cancel each other out. So this entire molecule, if you look at it as one object, is actually non-polar. It does not have a net dipole moment. So here we've got a non-polar, here we've also got a non-polar. So when you have two non-polars, then the intermolecular force between them is called London. Okay? Now, okay, so obviously I'm going to show you how to answer the question, but I'm just giving you the theory or the explanation right now. So London forces are between this one, okay? So we can say London. Now, what I just realized is that all of these are going to be non-polar. Check it out. If you have CCl4, that's also going to cause all of them to cancel out, right? Oh no, these electrons would actually go this way, but they would still cancel. Okay, you can go check it out for yourself. And then if you had CF4, the electrons are going to go outwards, but it's all going to cancel out. So all of these are non-polar molecules. So what is going on here? Well, this is actually a good question. Let's go explain. So, can we agree that all of these are non-polar molecules? Yes. So, there are London forces between this one's molecules, London forces between this one's molecules, and London forces between this one's molecules. So imagine life was so simple that all London molecules have a boiling point of -50 and all hydrogen bonding molecules have a boiling point of like 70, but it doesn't work like that. Even within the London forces, there are going to be different strengths. So what affects that? Well, scientists have observed, or they have been able to study this, and they have come up with the following, or they found the following. Heavier or larger molecules have stronger London forces. Okay, but now let me try to remind you exactly what London forces are and what causes them, okay? So we said that London forces take place between non-polar molecules. So let's draw the most basic non-polar molecule we can. We just make up a molecule called AA, and it's got a bond. Now, it's not more positive or more negative. Actually, let's just say it's got those electrons there. And then let's put another one. Now, electrons are not perfectly standing still. They are constantly moving, okay? Electrons are moving. So, what if for a few split seconds these electrons over here are a little bit to the left-hand side? Just a little bit. That would mean for that few split seconds that this one is becoming more negative, leaving this one to be more positive. And what if in this molecule over here, the same thing is happening, where these electrons go a little bit to that side? They're moving at all times, okay? So for a few split seconds, maybe this side is then the more negative, and this is the more positive. Suddenly, these two molecules are going to attract, because the positive over here would attract the negative, and the negative would attract the positive. Then, in the next split second, maybe the electrons move a little bit to this side. What that would then do is it would cause this side over here to become more negative, and this to become more positive, and maybe these electrons switch the other way, or maybe they go further this way. So this becomes even more negative and even more positive. Then there's going to be an attraction over there. That is what London forces are. They are temporary. Okay? They are not permanent, like what we have with dipole-dipole. They are temporary because these electrons are constantly moving. Okay. So that's the basics of what London forces are. But now let's say you've got large molecules or heavier molecules. Now, if you look on your periodic table, then what we can see is that the heavier molecules are the ones, if you look at the mass, 23, 24, 27, 28. These are heavier molecules as we start going down on the periodic table. With those, we are also having more electrons, because here you've got 12 electrons, here you've got 13 electrons, 16 electrons, 34 electrons, 35 electrons. You see the amount of electrons are becoming more. And so let's conclude that heavier molecules means more electrons. Okay. Now, you know what I showed you now with the London forces, and we said that it's because it's these electrons that are temporarily moving a little bit to that side and a little bit to that side. Now, when you have heavier molecules, you have more electrons. When you have more electrons, you increase the chance that this type of thing can happen. Because it's not only the electrons in the middle that are doing this. So let's say you have, for example, CH4, okay? So with CH4, that's how many electrons you have. Okay, that's the Lewis diagram. So you've got 8 valence electrons, and those 8 valence electrons can move around and cause this part to become a little bit more positive, this part to become a little bit negative, as these electrons are vibrating, because remember, these electrons are not standing still. Then if you have CF4, you can go check this out for yourself, but the Lewis diagram of CF4 is like this. You've got these electrons on the outside. Now, because you've got more electrons, there's more chances for these random movements to take place, and so you've got more of these positives and negatives happening more. There's more chance of them happening. And so if you have 2 CF4 molecules next to each other, there is going to be stronger attraction between these 2 molecules, because at any given moment there is a higher chance that this molecule and this molecule has like a lot of positives and negatives taking place, because there are more electrons moving around randomly, creating those positives and negatives. Whereas if you had this molecule and another one, there is less chance of creating positives and negatives in this one over here. Okay, so I hope that makes sense. Heavier molecules means that there's more electrons, and with more electrons you've got more of that random movement taking place, and then you've got therefore more chances of London forces, and so the overall London forces become stronger, because maybe in this molecule here you've got a slight positive and a slight negative happening over here. So there's an attraction, okay? But in this molecule, or in these 2, this one and this one, you might have a positive or negative here, a positive there, a negative there, a positive there, a positive there, a negative there, blah, 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 blah. And so you've got much more attraction taking place at any given moment. So heavier molecules, more electrons, more chances of these random asymmetries to take place, and so there's going to be stronger London forces. Okay, so if we now go and look at the masses, so if you look at CH4, it's going to be a carbon which has a mass of, where's carbon here, 12, and then there's 4 hydrogens. That one would have a mass of 16. CF4 would have a mass of 1938, 76. plus 12, so it's at 88. And then CCl4, ooh, that's a heavy one. Okay, so 35.5 multiplied by 4 plus 12 is 154. Okay, so we can see that the heaviest one, remember, heavy, more electrons, more chances for those temporary dipoles to take place. You can see it's got the largest boiling point. Now, some of you are like, yo, but bro, this one's 182, this one's 23. Guys, there's negatives. So that's negative 182. So that's much colder than this one, okay? So this one has a much larger melting point, sorry. Because remember that when you have CCl4, okay, so let's put CCl4, and then let's put another CCl4. Okay, now remember there's a whole bunch of electrons. So we said that because of all those electrons, there's going to be lots of positives and negatives, and so there's going to be a lot of London forces taking place over here. So if you have all of these London forces, it's going to be quite difficult to separate these two molecules from each other. And remember, when you melt, you are going from a solid where everything's close together to a liquid where everything's a little bit further apart. So to be able to melt something, you have to be able to overcome all of these forces. You've got to be able to separate these molecules from each other. So if the molecules are really heavy and there's lots of electrons, that means that there's lots of these temporary dipoles happening, and so the London forces are quite strong, and so you need more energy to be able to separate them. Now, what do we use for energy? We use temperature. The more hot you can make it, the more energy you have. So that is what they're saying here, is that if you would like to separate CCl4s from each other, you have to make it hotter than when you want to separate CH4s. Because with CH4s, some of you are like, oh, Kevin, you're going to go draw this all again. Come on, bro. Sorry, guys. I just really want to explain this nicely. Come on, Kevin. So with CH4s, there aren't as many temporary dipoles, so you don't need as much energy to separate them, and that's why the melting point is not as high as you have it for CCl4. Okay, so we can say something like all molecules in the table are nonpolar. Okay, so they will all contain London intermolecular forces. London forces increase in strength with an increase in molecular mass. Okay, we now need to just say that we can say that CCl4 mass is larger than CF4, which is larger than CH4. Okay, so we can say something like, therefore, the melting point of CCl4 is larger than CF4, which is larger than CH4, as more energy is needed to overcome the stronger intermolecular forces. This one says, which molecule in the table will have the highest vapor pressure? Okay, so let's talk about vapor pressure for a little bit. I want you to think about vapor pressure. Think about vapor. Is it liquid, solid, gas? Well, that's more of like a gas. So if you have a room, okay, that is filled with a lot of gas, then we would say that it has a very high vapor pressure. If you have a room that has a very little bit of gas, and most of it is in the liquid phase, and there's only a little bit of gas, then we would say low vapor pressure. Vapor pressure is for gases. So if there's a lot of gas, so lots of gas, then we say high vapor pressure. Okay. So if there's lots of gas, high vapor pressure. If there's a little bit of gas, then there's a low vapor pressure. So you need to think about which of these molecules are going to be easier to turn into a gas. Well, remember, to turn something into a gas, you have to first take it from a solid where the molecules are very close together. Then you have to separate them a little bit so that they become a liquid. And then you need to be able to separate them even further so that they become a gas. So we said that CH4, did we say that the London forces are stronger or weaker compared to CCl4? Well, if you remember correctly, we said that these ones over here have the weakest the weakest London forces. Then it's these ones, which are a little bit stronger, and then these ones are the strongest. Remember, because of the size and the mass and the electrons. So which ones are going to be easier to pull away from each other? Because remember, if you have two CH4s next to each other, okay, we said that because there are not that many electrons, the temporary London forces are not going to be that many. So you might have like, you won't have too many. So to be able to separate this is not going to be very difficult. Okay? Whereas, now don't worry, I'm not going to go draw the whole thing, but if you have like CF4 or CCl4 actually, and you had all those, okay, I'm just going to quickly do it. If you had all those electrons, right? These ones are going to be very difficult to separate because there are so many temporary London forces happening. So, these ones are easy to separate. These ones are very difficult to separate. So, if you had to walk into a room filled with CH4, you would probably find more gas. Because remember, to make a gas, you have to separate the molecules from the solid to the liquid to the gas. So, because these ones are easier to separate, you would find more of these in the gas phase. Whereas these ones over here are difficult to separate, so most of them are going to be in the solid or in the liquid phase at a certain temperature, if that makes sense. So you would expect the vapor pressure of this one to be more because there will be more gas at a specific temperature of this one. Okay? So it says here, which molecule on the table will have the highest vapor pressure? We will definitely say CH4. And that is just because it has the lowest melting point. Okay? Because they said explain by referring to the data in the table. So we can just say it has the lowest melting point. Okay, water is a smaller molecule than CCl4. What that means is they're trying to say that it is lighter. So it has less electrons. Water is only 18 grams per mole. Whereas this one we said was like a huge amount. Remember, it was like 154 grams. But water has a higher melting point than CCl4. Explain this observation by referring to the type of intermolecular forces. Now, I'm so happy they're including this question because we said this one has a mass of 16. We said this one has a mass of, I think we said 88. And then you've got water, which has a melting point. What is the melting point of water? Do we know? Yep, it's 0. When you go from ice to water, it's 0. Water is only 18 grams. Now, Kevin, I'm confused, brother. You told us that as the mass increases, the melting point increases. So if you had 18 grams over here, then surely water should be somewhere in between 182 and 150, negative. But that argument that I was showing you guys, where I was showing you all of those electrons and everything, I was talking about London forces. That is a property of London forces. London forces become stronger the heavier the molecule because of all of those electrons. But water is not only London forces. We need to remember that water is a polar molecule, so it has got London forces. All molecules have London forces. I wonder if you knew that, because there's always going to be electrons that are moving around. But water also has, because it's a polar molecule, it also has stronger intermolecular forces. In fact, water has hydrogen bonding, which is extremely strong compared to London forces. So even though CCl4 is a much larger molecule and it's got much stronger London forces than water, water is still going to be stronger due to the hydrogen bonding, because hydrogen bonding is much stronger than London forces. So it says, explain this observation by referring to the type of intermolecular forces. So we can just say that water has hydrogen bonding. And you could also say it's got London forces. Every molecule has London forces, because London forces simply arise due to the movement of electrons, and all molecules have electrons. So water has hydrogen bonding and London forces, whereas CCl4 only has London forces. This one says, write down the name of the intermolecular force that will exist if you had a mixture of H2O and CCl4. Okay, so let's put an H2O molecule over there, and then let's put a CCl4 molecule. Okay, so we know that this is a nonpolar, and we know that this is a polar. So what do you get when you put a polar next to a nonpolar? Well, you get a dipole, because this is a polar molecule, and we call that a dipole, and then we call it a induced dipole. Okay, we have studied that before, right? When you put a polar next to a nonpolar, you get a dipole-induced dipole. But what does that actually mean? Let me explain. What it means is that we definitely know this is polar, so it's got all these positives and these more negative parts, like that, okay? Now, with this molecule, it is overall non-polar, so there's no more positive part and more negative part. Overall, it is just completely neutral. So what happens is that when this water molecule comes floating along, okay, let's say for example the water molecule comes floating along like this, and it's got its negatives and its positives, then what would happen is that these electrons around here, or actually all of the electrons, as soon as this water molecule starts approaching with these positive parts facing like that, you would find that a lot of the electrons would start going towards that area because of just the opposites attract. So what happens is that this area of the this area here of the CCl4 is going to end up becoming very negative. Why? Because all the electrons are gathering over here, and it's going to leave the other areas in a more positive kind of way, because they're losing electrons. So what that means is that while this water molecule is in the area, it will cause this molecule to actually become a polar molecule. Okay? Because it's got a more negative side and a more positive side now. So we say that you have a dipole molecule inducing a dipole in another molecule. So it's called a dipole-induced dipole. And then as soon as this water moves away again, then all of this will just go back to normal. Okay? So this is just a temporary dipole. So we will split these questions up onto individual pages. So let's just read here. A group of learners investigate the relationship between pressure and volume of a gas at room temperature. They recorded their results. Okay, so here we have it over here. Okay, so let's go split the questions up. So the first question says, write down the name of the gas law. Okay, so we have 3 gas laws in grade 11. We've got Boyle, Charles, Gay-Lussac. The one that deals with pressure and volume is Boyle's law. Okay, so that is Boyle's law. Okay, what is the controlled variable? The variable that is not changed. Remember, you get independent, you get dependent, you get controlled. The independent is the variable that the human changes. Then they do the experiment, and this one then changes depending on what the human changed. So let me try explain that. The human comes along and changes one of the variables. Maybe they make the pressure larger. Then because of that, it causes something else to happen. Maybe the volume becomes less or something like that. And that is what the dependent variable is. And then the variable that never changes is your controlled. So we know that in this chapter, the main components are pressure, volume, temperature. So if Boyle's law is all about pressure volume, then temperature has to remain constant. So temperature would never change, and so we'll say here, temperature. The next question says, it says, for this investigation, write down the relationship between pressure and volume of the gas as described by the first 3 data sets in the table. Okay, so what we can see is that as the pressure is increasing, can you see the pressure is increasing? What is happening to the volume? The volume is decreasing. So we can say the pressure and volume of a gas are inversely proportional. What that means is that if the pressure, for example, goes up, then the volume goes down. Okay? So that is called inversely proportional. If they both go the same, so if one of them goes up and the other one goes up, or if one of them goes down and the other one goes down, that is called direct proportion. So here we need to calculate the value of x. So we know that when it's Boyle's law, then we would use the formula P1 V1 equals to P2 V2. Okay? And so what you can then do is you may choose any one of these pressure volumes for this part over here. It doesn't matter which ones you choose. You could choose that, you could choose this row or this row. Okay? I'm just going to choose the top row. We don't need to change any units. The only time you need to change units is when we use the formula PV is equal to nRT, which is the ideal gas formula. So here we're going to say 100,33, and then the volume is 7,34. The pressure 2 we don't know, so we'll call that X. And then the volume that goes with that one is 6.97. Now you can just get X by itself by just saying this side over here over 6.97. And so if you had to work out X, you should get 105.66. Now use the units, because we didn't change any units, just use the units that they have. So that'll be KP, or capital P, KPA. This next question says, write down the 2 conditions under which real gases behave like an ideal gas. Now, I don't want you to memorize this, because with careful understanding here, you will just know this. Think about this carefully. The word ideal means like it is perfect. So we want to think about a perfect gas, okay? Now let's think about gases. Remember, you get 3 phases in life. Well, main phases. You get solid, liquid, gas. In the solids, the molecules are very close together, okay? In solid. In liquid, they are a little bit further apart. And then in gas, they are very far apart. Okay? So gas molecules are far away from each other. So what we do, so gases things will behave like an ideal gas at high temperature. Let me explain why. Because what types of forces do we have in between these molecules? Well, we have intermolecular forces, dipole, hydrogen, London. And those forces are trying to pull the molecules together, okay? If the molecules have enough energy, though, then they can break, or they can, some curriculum, especially the IEB, they don't like you to use the word break, but they can overcome that attraction force that is between them, okay? They can overcome that attraction force because they have enough energy. Because remember, the intermolecular forces are trying to pull the molecules together, but if the molecules have enough energy, they can pull away and they can be separate. So when you have a high temperature, then remember that is a measure of the kinetic energy. So if the molecules have a lot of kinetic energy or a high temperature, then they have the energy to overcome the forces of attraction, and so they can move further away. Whereas when they are at a low temperature, they don't have enough energy, and then they get pulled closer together by the intermolecular forces. So for something to be a gas, you want to have high temperature. Okay, the next thing we're going to talk about is volume. So you see with solids, you see how they're very close together. Okay, so there's like a very small volume. With liquids, they're a little bit further apart. Okay, and then with gases, they're very far apart. So this is solids again, liquid, and gas. So there's your solid, there's your liquid, and there is your gas. So gases, they do well when there is a low pressure, high volume. So they want high volume because that allows them. So they don't want you to put them under high pressure, because as soon as you put them under high pressure, then that means you're making the volume smaller, and suddenly you're pushing the molecules closer together, and then they're going to start attracting each other, and they might start turning into liquids and solids. So gases love large volumes. So what we'll say is they love low pressure. We don't talk about volume really. We rather say that they love low pressure. Because remember, when the volume of a container is very big, then the pressure is very low, because pressure is when the molecules are bumping into the sides of the container. Now, if the container is very big, or if the volume is very big, then the pressure is going to be very low. So if you want something to behave like a gas, give it high temperature and give it a very low pressure. And then this question over here says, write down the name of a gas whose behavior is very close to that of ideal. So remember, in real life, we have real gases, but the scientists who discovered this stuff, they came up with the perfect model, which they called ideal. Now, there is no gas in real life that is perfectly ideal, but there are some gases that come very close. And those are going to be the top two gases on the periodic table, which is hydrogen, because they're very, very small molecules, and helium. Those are the two gases that are very close to ideal. Okay, so you only have to name one of those. This question says that an organic compound has the following composition by mass. Okay, so they give us the composition by mass, and then they say the molar mass is twice the empirical molar mass. So let's quickly remind you empirical and molecular. So let's say you have an empirical formula of C3H7O4. Can these numbers be simplified? No, they can't. That is why we call this the empirical formula. It is the most simplified ratio that you can get. Now, the molecular mass would always be a multiple of that. So maybe it is triple. So maybe it's C9H21O12. So maybe this is the molecular mass, which is what it looks like in real life, but this is the simplified mass. Okay? So in this question, they said that it's twice. So this would maybe become like C6H14 and O8. Now, if you had to simplify this, you would just go back to the empirical. Okay, so I hope that reminds you the difference between empirical, molecular. Empirical is the simplified one. The molecular is not simplified. Okay, so the first question says, define the term empirical formula. So it is the simplest whole number ratio between the elements of a compound. So these are just the simplified, this one over here. It's the simplified whole number ratio of all of the elements. Okay? Now the next question says, for 5 marks, determine by calculation the molecular formula. Okay, so we first use this to get the empirical, and then we use extra information, such as this, to get the molecular. Okay, and this is easy marks, guys. Molecular empirical formula, it's just a specific way you got to do it, but it's usually not that difficult. Okay, so let's go through the steps. So you would definitely need a periodic table. but I'll just give you these masses. So on the periodic table, carbon is 12, hydrogen is 1, oxygen is 16. Okay, so the first thing to do is to realize that they told us that these are the percentages by mass. Now, what we do is the following. If you add all of these numbers together, what should it give you? Well, 100, because percentage always adds up to 100. So what we will rather do is we will just pretend that this is not percentage. Let's rather pretend that it's grams. Okay, so that means that we then have 54.55 grams of carbon. It then means we have 9.09 grams of hydrogen. Okay, and then for oxygen, that would be 36.36 grams. The next step is to convert each of those into moles by using the N equals to M over capital M formula. And so for carbon, that would be 54.55 over 12. For hydrogen, that would be 9.09 over 1. And for oxygen, that would be 36.36 over 16. Okay, now if we go calculate each of those, we end up with 4.54. You can just keep 2 decimals. It's really not that important with this part. And then for hydrogen, you're just going to get 9.09. And then for this one over here, you're going to get 2.27. What we then do is we take the smallest number, which is going to be the 2.27. And so you're going to divide all of them by that number. So you're going to say 4.54 divided by 2.27, which is 2. Then you're going to say 9.09 divided by 2.27, which is pretty much 4. And then you're going to say 2.27 divided by 2.27, and that is 1. And there are your answers. Okay? So what it means is that we are going to have C2H4O. That is the empirical formula. That is your empirical. Okay? But now they told us that the molar mass of the actual compound, which is the molecular, is twice the empirical. So you're going to double each of those. So the molecular is then going to be C4H8O2. You see how we multiplied each of those by 2. So C4H8O2. Okay, if you are using the memo of this exam paper, they did make a mistake. When they calculated this part, they said the answer is 3. Okay, but you can go double check that for yourself. It is exactly 4. Okay. All right, now this question will be split up. I know it's not very clear, but I just wanted you to see all the questions. So there's one here, one here, one here, and one here. Okay, but let's go split it all up. So here a teacher demonstrates to a group of learners the impact of limiting reagent on the amount of product form in a chemical reaction. The teacher uses the following equation. Okay, so they love to use this hydrogen producing one. Remember, that's when you take a metal and an acid. What does a metal and an acid give you? It gives you the salt and gas, or hydrogen gas specifically. So it says the teacher uses the following setup. Okay, so we've seen this before, right? What they do is they take the zinc, they react it with, now the zinc is in the solid phase, they react it with the liquidy HCl, which is in the aqueous phase, and that reaction produces a gas. The gas would obviously rise, and they collect the gas in a gas syringe, and that's how they can see how much gas is being collected. Okay, so here we are told that there are 2 experiments. In experiment 1, we use 7 grams of zinc and 1 mole of HCl. In experiment 2, we use 3.27 grams of zinc and 1 mole of HCl. The first question, define the term limiting reagent. Now remember, if you have a chemical reaction, let's say you put a whole bunch of A and you put a whole bunch of B, and let's say that A is limiting, then that means that B is excess. What that means is that after the reaction is finished, there will still be a little bit of B left over because there was too much of it, but all of the A would have been used up. You see, there's no more A left over because the limiting reagent is the reactant that is completely used up in a chemical reaction. Okay, it's the one that is completely used up in a chemical reaction. So this next question says determine by calculation the limiting reagent in experiment 1. Okay, so we're going to do this on another page because I want us to spend a good amount of time here. So here we've got the details for experiment 1, and here we have the reaction for this, that's taking place in this experiment. So with limiting reagent, step one, just get both of these in moles. Okay, so you need both of those in moles. So we've got this one in moles, but we need to get this one into moles now. So we can, so we're going to need the periodic table, so we can get the mass, the molar mass of zinc, which is 65. So then we can use the formula N equals to, or let's just say as step 1, get moles of both. Okay, so N equals to M over capital M, which is then going to be 7 over 65, which is, I'm just going to keep about 4 decimals, 1076 moles. Okay, so we know how many moles of zinc we have. We have 0.1076 moles. Now what you do, okay? Assume one of them is the limiting. So what we're going to do is we're going to pretend, what we do in this whole section with limiting reagent is we pretend that one of them is limiting, and then we do a calculation to see if that assumption that we made is correct. Okay, so it doesn't matter which one you choose. So you're either going to choose the zinc or the HCl. So what would you like? Okay, well, Kevin, you can't ask people what they like when it's a video where you're only talking, bro. Okay, sorry. So let's assume that zinc is limiting. Okay, so we're pretending that zinc is limiting. What is the limiting reactant again? It is the one that you use up completely. So that means we are going to use up all of this, but we're not going to use up all of this. So what that means is you can't actually use this number because we don't know how much of it we're going to use. But we are going to use up all the zinc because it is the limiting, and when it's the limiting, it means you use all of it. So the amount of zinc that we would use would be 0.1076 moles. So then how much HCl would we use? You can't say 1. You cannot say 1. What you do is you use the ratio in the reaction. So we know the ratio is 1 to 2 for zinc to HCl. Now we know that the zinc here is 0.1076. So what we will do is we will just multiply that by 2. So the amount of HCl that we would use is going to be 0.1076 multiplied by 2, and that would be 0.2152. Now what we do is we think about, does this make sense? Can we use all of the zinc and then we only use 0.2152? Let's see how much HCl we actually have available. Oh, yes, we have more than enough. We have 1 mole, and they're telling us that we only have to use that amount over there. So this actually works out perfectly. So it means that zinc is limiting because there was no problem. Kevin, I don't understand. That's probably what some of you are saying. Okay, fine. Let's do it the other way around. Let's assume, okay, but let me first just say here, because this one was perfect, there were no problems here, we can say therefore zinc is the limiting one. Our assumption was correct. Let's say we assume the other way around. What if we assume that HCl is limiting? Okay, then that means you cannot use this number because we don't know how much of this we're going to use, but what we can do is we can use this number. Because remember, if HCl is limiting, then it means we use all of it, okay? So that means, but now we can't use this number because that's not the limiting reactant anymore. You see how that works? So the amount of HCl that will be used will be 1 mole. So then the amount of zinc, you're not going to use this number, you're now going to use the ratio. So we know that the zinc to HCl is 1 to 2. So if this is 1 mole over here, then we got to figure out that. So that means you're going to end up saying 1 divided by 2, because you see the amount of HCl is always double the amount of zinc. So if we're using 1 mole of zinc, if we're using 1 mole of HCl, then that means we are going to use 0.5 moles of zinc. But now that is not possible. We cannot use 0.5 moles. Why? Because in the beginning of the experiment, we only have that amount to be able to use. So you see, this number is fine, but this number does not work. There's not enough of this. So what we then do is realize that there's something wrong here. So what we then look at is that this one over here works. And let me show you why. Because we said here that we're going to use 0.1076 moles, and there we can see that number is perfect. And then we said we're going to use 0.2152 HCl, and we do have enough, you see? So it's as long as you have enough. So in this scenario, we have enough, but in this scenario, there was a little bit of a problem because the zinc was 0.5, but we only have 0.1. So there's something wrong with this one, and so it cannot be that HCl is limiting, and so it has to be that zinc is limiting. Okay, now this question says, how will the amount of zinc chloride produced in experiment 2 compare to experiment 1? So let's just remember that zinc is limiting. Zinc is limiting. What that means, or let's say, how will the amount of zinc chloride, okay, so zinc chloride is one of the products, produced in experiment 2 compare to that of experiment 1? Well, we know that zinc is limiting. And if you wanted to go redo the calculation for experiment 2, you would find out that zinc is still going to be limiting. That means that this experiment will stop when the zinc has run out. So here you started with 7 grams of zinc. So would you agree with me that that reaction 1 would produce more products, because the reaction would only stop once you have used 7 grams of zinc. So you can see that the zinc and the zinc chloride, they are in a 1-to-1 ratio. So however many moles of zinc you use, that's how many moles of zinc chloride you would be able to produce. So in this reaction, you've got less zinc. Okay, you've got less zinc. So that means the moles of zinc over here is going to be less, and so the zinc chloride is also going to be less because they are in a 1-to-1 ratio. So the amount of zinc chloride is definitely going to be lower. Okay, and then our reasoning, because it's for 4 marks, we can just say zinc is limiting. So we say as experiment 2 uses less zinc, then it means less zinc chloride will form. This question says that experiment 2 was carried out at 40 degrees. The molar volume of hydrogen, so the molar volume, is 25.7. Now let me talk about that. Normally this question would have said STP, which we know is then at 0 degrees Celsius, okay, and and like 1 atmosphere. So that's okay, and at that temperature, we usually say that the volume of 1 mole of gas, if it's a gas, is 22.4 decimeters. Okay, but now that the temperature is a little bit warmer, the gas expands a little bit, and so this is why we are not using 22.4, because that's only for STP, but instead they've asked us to please use 25.7. So you know in that formula where you go N equals to V over Vm, Vm is molar volume of gas, which in this question is going to be 25.7 and not 22.4, which is when we only have it at STP. Okay, hope that makes sense. So calculate the volume, and remember that 22.4 is only for gas, and remember this hydrogen is a gas. Some learners, when they use this formula, which is for liquids, they try use 22.4 here, but that's not correct. That's for liquids. When we're talking about gases, we typically use this formula, and then you use 22.4 there, if it's at STP. So it says here, experiment 2 was carried out at 40 degrees. The molar volume of that is that. Calculate they're not saying that the volume of hydrogen is that. They're saying it's molar volume. So that means it's that per mole, okay? So so it's just know that this 25.7 is the Vm. Okay, it's not the V. So it says calculate the volume of hydrogen gas, which is this, produced once the reaction reaches completion. Okay, very easy question. We know how much zinc we used, okay? So we can work out the moles of zinc over there. Then we can simply use the mole ratio from zinc to hydrogen to get the moles of hydrogen, which would be this number over here. So then we would have this number, and we would have this number, and then we can easily get that number. Okay, so from our periodic table, we know that zinc has a mass of 65. So we can say N equals to M over capital M. So we can say N equals to 3.27 over 65. And that gives us, okay, we can round this to 0.05 moles. Okay, now we can look at the ratio in our balanced equation. Make sure it is balanced, but it is, because there's a 2 over there, so we know that they've done some balancing, but always make sure, okay? So what we can see is the ratio between zinc and the thing that we are looking for, which is hydrogen, is in a 1-to-1 ratio. So that means if we have 0.05 zinc, then your hydrogen is going to be 0.05. Okay? Now we can use our formula where we know the moles. We don't know the volume, but we know the molar volume that they've asked us to use is 25.7. So remember that, hey, this is molar volume. It's not volume, it's molar volume. So it's the Vm, okay? And then if you just take this and you multiply it up to the top, you're going to end up with the volume as, if you round that up, and you are going to get that as 1.285, and that would be in decimeters. Consider the following ionization reaction of HCl. So HCl plus H2O gives us Cl minus and H3O. Okay. Define an acid in terms of the Lowry-Bronsted model. Okay, so remember we've got Arrhenius and we've got Bronsted. So let me quickly summarize this for you in case you're studying for like a test or whatever. So we've got acids and we've got bases. Okay, and then we've got Arrhenius and we've got Bronsted. So for acids, Arrhenius says that an acid would be something like it's actually like this. Remember, you can sometimes get Bronsted and Arrhenius in one. So an acid is something that when you react it with water, or when you dissolve it in water, it produces hydronium, or H3O+. So we can say that that's what Arrhenius said, produces H3O+ in water. Arrhenius was all about water. Okay, then what did Arrhenius say about base? Well, Arrhenius said that if you take a base and you dissolve it in water, it produces OH minus. Okay, so we can say here produces OH minus in water. See, that dude was all about the water. Okay, now Bronsted, his definition was a little bit more usable, and what he said was that an acid, okay, I don't have to say that, is a proton donor. So it donates a hydrogen, okay? Or it donates a hydrogen ion, okay? So we can just say here, gives H+ away, okay? And then a base, a Bronsted base, accepts H+. So it is a proton receiver. Okay, so, and you can get more than one. Like, for example, something can be a Bronsted and an Arrhenius acid. Remember, these are two scientists who came up with definitions. So there are some places where their definitions will work out together, and then there will be other times where they won't work out. Okay? So this one says, define an acid in terms of the Lowry-Bronsted. So we can say that an acid is a proton donator, or a proton donor. This question says, write down one conjugate acid-base pair. Okay, so what we need to understand about conjugates is that it's the same molecule. Just look for the same molecule, but with one less or one more hydrogen. So it's the same molecule. Okay, so where do we see the same molecule over here? Well, you could see that one and that one, because there's one hydrogen extra over there. Or you could use these two, and you would see that there's one hydrogen extra over here. So your answer could either be the H2O and the H3O. They are one pair. You see how it's the same molecule, but there's just one extra hydrogen on one of them. And then your other answer that you could have used would be HCl and Cl minus. Can you see that they are all the same, but there's just one hydrogen less or more on one of them? Okay. Write down the formula of a substance, or the substance in the reaction that can act as an ampholyte. It's actually water. Water is an ampholyte. Well, Kevin, what is an ampholyte? An ampholyte is a substance that can act as a base, and it can also act as an acid. Okay. How can it do that? Well, if water acts as an acid, so remember what an acid does. It gives away hydrogen. Gives, or it donates hydrogen. So if this thing gives a hydrogen away, then it's going to have one less hydrogen, but you don't write it like that. You rather write it as OH, and then it would have a negative charge, because here it's neutral, right? Then it gives away a proton, which is a H+. So if you give away a positive, then you become more negative. Okay, now if it acts as a base, then that means it receives a hydrogen. So that means the H2O would then end up becoming H3. There would now be 3 hydrogens, and now it's receiving something that's positive, so this molecule will become more positive. Okay, so acids, water is an ampholyte. It can act as an acid and a base. Ooh, so here we have a nice acid-base reaction with a 7 marker coming our way. I will split these up onto different pages, but let's just read. A certain volume of... Now, I'll be honest, these acid-base questions, they do give learners trauma, but there's usually a specific way, not a specific way, but usually there's a specific place where you start, and it's usually easy to find that place, and then you just go from there, okay? Just follow me and see, and I'll show you what I'm talking about. A certain volume of hydrochloric acid of concentration, this is added to a sample of seashells of 8 grams, okay? The hydrochloric acid completely reacts with the calcium carbonate, okay? So the HCl gets used up completely, according to the balanced equation. Okay, so we've got some, now think about this carefully. You've got some seashells, okay? Now, those seashells contain, so there's your seashells. Now, some of that, they said the seashell contains 95%. So 95% of the seashell is CaCO3, and the other 5% is just, other stuff. Okay, so that is your seashell altogether. There's a big seashell. Now, 95% of it is calcium carbonate, 5% of it is other stuff. Now, what they're going to do is they're going to add acid onto the seashell, okay? Now, remember, the other stuff doesn't do anything. It is the calcium carbonate that is going to do the reacting, okay? The calcium carbonate is what reacts, and we can see that over here, okay? So remember that this part here is not the whole seashell. That's just the CaCO3 in the seashell, okay? Now it says that the seashell contains 95% calcium carbonate. Okay, first question, is the reaction endothermic or exothermic? Well, that just has to do with this over here. You need to know this by theory. So when it's smaller than 0, that's exothermic. When it is larger than 0, when it's positive, that is endothermic. Okay, so you just got to remember that. So this one would be exothermic. Now they say give a reason for your answer. So how did we know that? Well, we know that because delta H was smaller than 0. Okay, so this question says calculate the volume in centimeter cube of the hydrochloric acid that was added to the sample inside the container. Okay, so let's see what we have here. We have a container filled with seashells. Okay, how many seashells? Well, how much? 8 grams. Okay, but remember that not all of it's not the seashell that reacts with the acid, it's the calcium carbonate that is in the seashell. So remember that 95% of the seashell, 95% is calcium carbonate. Then they are going to take some HCl, okay, and they are going to throw that inside here. Okay. So what we can quickly go do is let's go see how much calcium carbonate we actually have. So we can just say, okay, we know that the seashell is 8 grams. So why do I keep doing that? So let's go work out what is 95% of 8. So you could just say 95% on your calculator, or you can say 95 over 100 multiplied by 8. And that's going to give you 7.6 grams. Okay, so now check this out, guys. Look how easy this actually is, okay? So we know how much mass of calcium carbonate we have. As soon as you have mass, you can get moles. Once you have moles, you are in business. Because once you have moles, then you can get any one of the others by just using the mole ratio. Once we have the mole ratio, once we get that, we can get the moles of HCl. Check here, we also know what the concentration of the HCl is. When you have moles and you have concentration, then you can work out volume. Hello, it's not that bad. So we are going to say, okay, N equals to M over M, so we can get the moles of CaCO3. Now we need a periodic table. Okay, we could get a periodic table, or I'll just help you out quickly. So calcium on the periodic table is 40. Carbon is 12. Oxygen is 16. So if you want to get the molar mass of CaCO3, it's going to be 40 plus 12 plus 3 times 16, and that would be 100. So we could say the moles is going to be 7.6 over 100, and that would end up being 0.076. Okay, and that is calcium carbonate. Now what you do is you come to the reaction and you look at the ratio 1 to 2. So that's so the CaCO3 to HCl is a 1 to 2 ratio. So if we know that this is 0.076 and this is X, so you see how the HCl is double. So that means we'll multiply this by 2. So X would then be 0.076 multiplied by 2. Because over here, I haven't actually explained this part nicely before. This part here, you can actually just use cross multiplication. So multiply that there and multiply that there. And so you'd end up with 1x is equal to 0.076 multiplied by 2. And so x is equal to 0.152. Okay, so now we have the moles of HCl. Okay, so now we can use this formula. C is equal to N over V, because now we have the concentration of the HCl, 0.5. And then the moles of HCl was 0.152, and then the volume is what we're trying to calculate. So just multiply this volume over to the left-hand side. I'm going to take this over here. So you would end up with 0.5 V equals to 0.152, and then if you get the volume by itself, you end up with 0.304. But that's in decimeters, but they want the answer in centimeters. So you multiply by 1,000, and so the volume would be 304 centimeter cubed. This question says, define oxidation. Okay, so oxidation is the loss of electrons. Where did I get that from? Oil rig. It tells us that oxidation is loss, reduction is gain of electrons. From the balanced equation above, write down the reduction half reaction. Okay, so we need to just look at the following. We can see that there is, let's go look at all the oxidation numbers, okay? So we know that the oxidation number of something that is by itself is 0. The oxidation number of something that has a charge is the charge, so that's just positive 1. This one is just positive 2, and this one will just be 0 because it's by itself. You see, it's got no charge. Okay, so we know that when these numbers here, so you see how the copper goes from 0 and it goes to 2, so it becomes more positive. That is oxidation. Because remember, oxidation is when you lose electrons, and when you lose electrons, you become more positive. Then this one over here is reduction, okay? Because you're going from a positive, and then you're going to something that is less positive. So the only way you can do that is when you gain electrons, because electrons are negative. Okay, so there we have reduction. Okay, so the reduction half reaction is going to be the Ag. So you're going to take the Ag plus, and you're going to draw an arrow, and you're going to say Ag. So you could actually just go find this reaction. So either you know where to put the electrons, okay, but if you have the standard reduction potential, which is something they gave for this exam paper. So it depends. Some schools in grade 11, they don't use the standard tables yet. They only use it in grade 12. But some schools are now starting to use it in grade 11. In fact, a lot of schools are. So either your teacher has taught you using the table, so then you can just go look at that, which I'll show you now, or you need to remember where to put the electron, okay? So let's go look at the table. Okay, and so this is the table. I'm using table 4b, and so here we can see the reaction over here. So we've got the Ag plus, there we have it, and then on the right-hand side we have Ag. So if you see where the electron needs to go, it's over there. So you would say plus E minus gives you Ag, and so that is your reduction half reaction. Okay, so you might be saying, Kevin, but why are there 2's over here? The 2's are there. That's only when you put the oxidation and the reduction reaction together. Then you need to balance it all out. Okay, but when you're just doing the individual one, then you just take it from the table. Okay, now what is the formula of the reducing agent? Right, now reducing agent and oxidation agent, they are only the parts in the reactants. So it's that part or that part. It's not the products, okay? So we said that this one was 0, this one was 2, this one was 0, this one was plus 1, and this one was 0. So we also said that this is oxidation, and we said that this is reduction. Okay, now the substance that is oxidized, so let's write this down. The substance that is oxidized is called a reducing agent. Okay? And then the substance that is reduced is called an oxidizing agent. Okay, so, and we said that it's only the reactants, okay? So, the reducing agent is the one that is oxidized. So, the oxidized one was this reaction over here, so it's the copper, okay? So, you are going to go say that it is the copper. Okay, for 1 mark, the explanation for your answer in 7.1.3 by referring to the oxidation numbers. Okay, so that's what a weird question, but just say that its oxidation number increases from 0 to 2. Like, that doesn't even have to make any sense, but just say that, okay? So the oxidation numbers increased from 0 to 2. Okay, that's why copper is the reducing agent, because its oxidation number went from 0 to 2. Okay, I will split this question up onto individual pages. So it says that the following incomplete chemical reaction is a redox reaction. The first question, let's split that up onto the next page. Determine the oxidation number of Cr. Okay, so we have Cr2O72-. Okay, so I've made videos on oxidation numbers. So the first thing we need to understand is that this overall molecule has a charge of -2. Okay, so we're going to say equals -2 over here. Okay, now there are 2 of these chromiums, but we don't know what its oxidation number is, so we can call it X. So we can say 2X plus. Now we need to go get the oxidation number of oxygen, so we need our periodic table. Okay, now if you look at oxygen, and we've spoken about this with redox numbers and all of that, but the oxidation number, remember it goes 1, 2, 3, 4, then it's usually -3, -2, -1. So oxygen is going to be -2, okay, but there are 7 of them. So you're going to say 7 multiplied by -2, and so you're going to end up with 2x plus, well actually this becomes -14 equals -2. And then if you take the -14 over, you're going to end up with -2 plus 14, which is 12, divide by 2, and you end up with x as 6. So the oxidation number of Cr is going to be 6. Alright, so this question says use information from the table of standard reduction potentials, which I will get now, and write down the balanced net ionic reaction. Okay, so you go look on your table, and you're pretty much just going to look for things that have Fe2 plus to turning into Fe3. So I went and found this one on the table. Don't go look for the other Fe on your table that has like a Fe2 and a Fe, because that's not what we have. What we have in our reaction is Fe2 and Fe3. Okay, so we take this one, and then we're going to look for stuff that has this and this, which I found down here. Okay, so now just be careful that you write it the right way. So you see how this is on the left? This is also on the left. So that reaction is perfect. So let's just go write that one down. Cr2O72- plus 14H plus 6 electrons gives us 2Cr3 plus 7H2O. You don't need to put a double arrow because we are only writing it in the specific way. That double arrow is just there to show you that it can go both ways, but for our particular reaction, it's going from left to right. Now, have a look here. We've got Fe2 plus on the left. Here we've got Fe2 plus on the right. So we need to switch this reaction around so it goes the other way. So it's going to go Fe2 plus. See, I'm starting there. Then it's the arrow. So we put the arrow. And then we say Fe3 plus E minus. Okay. Now you need to know which one is reduction, which one is oxidation. So remember that when we are plusing electrons on the left-hand side, that is called reduction. When we are plusing electrons on the other side, on the right-hand side, that is oxidation. Okay, because they told us, please indicate the reduction and the oxidation. We've done that. Now we need to balance it. So that's very easy. You look at the electrons. How many electrons do you have there? You've got 1. How many electrons do you have here? You have 6. What is the LCD? That would just be 6. So you can multiply this reaction by 6, and so you're going to have a 6 in the front, a 6 over there, and a 6 over there. Now you're simply going to add these two reactions together. Okay, you're just going to add them together. So you see how there's an arrow and an arrow. So let's just put that over there. Okay, so everything on the left-hand side of the arrow, let's go add that together. So that's going to be Cr2O72 minus plus 14H plus 6 electrons. That's over there. Now that's everything on the left side of that arrow. So let's move on to the left side of this arrow, which is just going to be plus 6Fe2 plus. Okay, then do an arrow. And then it's going to be 2Cr3 plus 7H2O plus 6Fe3 plus plus 6 electrons. Now, those electrons cancel out. That was why that's why we made the numbers the same, so that they do cancel out. And so that would be the final answer, where we've balanced the equation like that.